Hi everyone, this is Dr. G. Ravindranath Reddy working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So we are discussing numerical methods and integral transform course. In that course, we are at Fourier transforms. So in this video, we will discuss what is a Fourier transform, where we can use these Fourier transforms, or we can see the applications of Fourier transforms in the engineering field, and what is Fourier integral theorem, and what is Fourier sine and cosine integrals. And on this we are going to discuss some problems. So first we will take some introduction to these Fourier transforms. So in the previous videos we have discussed about the Fourier series, how to expand the Fourier series for the given function in that particular interval 0, 2 pi or minus pi, pi or 0, pi, and in the arbitrary intervals minus L to L, 0, I to L. So all these functions, whenever we apply the Fourier series, that functions are only periodic functions. For the non-periodic functions, it is not possible to use this Fourier series here. So in that case, we can, for the non-periodic functions or non-periodic signals, we can go for the Fourier transforms here. So to overcome this shortcoming, so Fourier developed a mathematical model to transform signals between time domain to frequency domain and vice versa. So this procedure we can call it as a Fourier transforms. So Fourier transforms has many applications, whereas in physics and the engineering, such as analysis of LTI, that is linear time invariant systems, radar, astronomy and signal processing, etc. So when you come to the applications of this Fourier transform, so we're having many applications in science and engineering. So among these are some applications we can see here. Applications of initial boundary value problems, circuit analysis and the signal analysis. We can also use this concept Fourier transforms in the cell phones, also in the image processing and in the signal processing and LTI systems. So these are some basic applications of this Fourier transforms here. So now, whenever we want to find out the Fourier transform for the function f of x, that function has to satisfy some conditions. So we can call it as a Dirichlet conditions here. Now we'll see what are the Dirichlet conditions. So a function f of x is said to have a Dirichlet condition set to satisfy the Dirichlet conditions in this particular interval alpha, beta. So whenever these two conditions are satisfied, then we can say that the function f of x satisfies Dirichlet conditions. So now we'll see what are the two conditions we are having. So f of x must be a well-defined function, and that f of x must be a single valued function, and at finite, so single valued functions in the interval alpha, beta, except possibly at finite number of points. So it may be discontinuous functions also. So one more thing is f of x and f dash of x are both piecewise continuous in the interval alpha, beta. We have seen what is maybe a piecewise continuous in the Laplace transform while you are discussing the Laplace transform. So these two functions f of x and f dash of x both must be a piecewise continuous in the interval alpha, beta. So these are the two conditions. The first one is f of x must be well defined and is a single valued function in the interval alpha, beta, and f of x and f dash of x, these two functions must be piecewise continuous in the given interval alpha, beta. So if these two conditions are satisfied by this function f of x, then we can say that that function f of x satisfies the Dirichlet conditions in that given particular interval. So now we'll go for the next one, Fourier integral theorem. So we'll see what is Fourier integral theorem. So by using this Fourier integral theorem, we'll see how to derive Fourier sine integral and Fourier cosine integrals. So this is the statement of this Fourier integral theorem. So f of x is equal to 1 by pi integral 0 to infinity integral minus infinity to infinity f of t cos p of t minus x dt dp. So this is the statement of this Fourier integral theorem. By using this statement, we are going to derive Fourier sine integral and Fourier cosine integral. Now we'll see how to derive this one. So now we are taking the Fourier integral theorem. So now here, once if we observe the cos function, so I want to remove these brackets by multiplying with p with t, and so you will get this as cos of pt minus px. Now this is of the form cos of a minus b. Use this formula, cos of a minus b, cos a cos b plus sin a sin b. So here you will get cos pt into cos px plus sin pt into sin px dt dp. So by using this formula, cos of a minus b, we have expanded this to this form. Now remove these brackets by multiplying with the f of t. So you will get f of t into the first term and f of t into second term. So you will get this one. So now by using this, so now apply the integration separately for each term. This is the first term, this is the second term. Now apply the integers in these two double integrals for separately for each term. So when we apply separately here, so 1 by pi integral 0 to infinity cos px. So here one integral we have to apply with respect to t, and the another integral we have to apply with respect to p. So now whenever suppose if you want to apply the integration with respect to p second, now keep this cos px outside since it is a constant. So we have seen how we know how to apply the multiple integrals, one with respect to one variable and next with respect to another variable. So now take integrals minus infinity to infinity f of t cos pt dt, and similarly follow the same procedure here. So first you complete this integral which is inside the brackets, and then we can go for the second integration with respect to p. Now we don't know the function, whether this f of t is an even function or odd function, and here also we don't know the function f of t is an even function or odd function. Why we are concentrating on even and odd function? Because the integral limits are minus infinity to infinity. So whenever we are having the integral limits as minus a to a or minus b to b or minus 1 to 1 or minus infinity to infinity, so in this case whenever with these type of integrals from minus to positive, then we have to concentrate on the function, whether it is an even function or odd function. Based on that we have the formula. If it is an odd function between the limits minus infinity to infinity, then directly we can take that integral value as 0. So already we know, we have discussed this in previous classes. So now this is our integral we got. Now I want to take the case 1 here. Case 1. So first I want to take the function f of t as an odd function. So I am considering in the case 1 I will consider that f of t as an odd function. Now already we know that f of t is odd function and cos pt, this is even function. So whenever we multiply odd function with the even function, then the resultant function it will be an odd function. So this entire function, so this function becomes an odd function here. Now next go to the next integration here, this one. So f of t, we have taken f of t as an odd function, and sine is an sine is an odd function here. So whenever we multiply both odd functions, then the resultant function will be an even function. So this function is an even function here. So the first integral in the right side becomes 0, because whenever we are having the integral of the form minus a to a and f of x dx, so whenever this function f of x is an odd function, then we can take that integral value directly as equal to 0. So if this integral value is equal to 0, then integral of the remaining function 0 into anything equal to 0, integral of 0 is 0. So this entire first integral, it becomes 0 in the case 1. Case 1 is whenever f of t is an odd function. So you will get only, we have to concentrate only on the second integral here, second part. And now, so now you consider the second part here. So whenever we get this, so whenever the function is an even function, then this integral can be written as integral 2 into integral 0 to a f of x dx. So 2 into integral 0 to a f of x dx. So you take 2 into integral 0 to infinity, that is the first integral. So you take that first integral, and this one, since it is an even function, based on this formula we have to take 2 into integral 0 to infinity f of t sin pt dt. Okay, so this we can consider as whatever we got the remaining integral, so that gives the Fourier sine integral formula. This is the Fourier sine integral formula we have derived. Now in case 2, so instead of taking f of t as an odd function, in case 2 you consider this as even function. Then we will get another integral formula that we can call it as a Fourier cosine integral. So now we will go for this case 2 here. So this is the resultant matrix, resultant integral we got. Now case 2, you consider that case 2 f of t as an even function. So now we are taking this as even function, even, and this is even function here. So now, so this is even function f of t, this cos is also an even function. So both, if you multiply two even functions, then the resultant function, the product of two even functions is always an even function here. So this entire function, it becomes an even function. Now go to the second integral. So f of t we have considered as even function, and sin pt, this is an odd function. Already we know that sin is an odd function. So whenever we multiply one even with odd function, then the resultant function, this entire function f of t into sin pt, this becomes an odd function. Follow the same procedure what we have followed in the previous. So since it is an odd function, this entire integral becomes 0. We can neglect this. So you will get only the first integral here. So this we can call it as 2 by pi integral 0 to, so this integral minus infinity to infinity, we can take it as 2 into integral 0 to infinity cos px integral 0 to infinity f of t cos pt dt dp. This we can consider as the Fourier cosine integral formula. So these are the Fourier cosine and Fourier sine integral formulas here. Now by using these Fourier sine and cosine integrals, we will take some functions and we will find out that Fourier sine integral value and Fourier cosine integral values here. Now let us take the problem here. Using Fourier integral, so we are having two types of Fourier integrals. One is Fourier sine integral and Fourier cosine integral. In the problem he has not mentioned the particular formula, so just he has mentioned Fourier integral. So we have two, so based on that two we have to decide one Fourier integral formula to prove this condition here. So this is the function, you consider this as a function f of x. So f of x is equal to, this is the condition what we have to prove. So the meaning of this one is, for this function the Fourier integral value is equal to, we have to prove this value here. So for this we have to decide whether we have to apply Fourier sine integral formula or Fourier cosine integral formula. Now we will see how to decide any one of these two formulas here by seeing that problem. So once you read this, so since the integrand is nothing but the function inside the integral, so on the RHS side contains s sine term here. So once if you observe this, the function which is inside the integral, this is the function we are having inside the integral on RHS side of this condition. So here we are having a sine function which is in terms of lambda into x. Now based on this function we have to decide whether we have to go for the Fourier sine or Fourier integral formula. So since in the integrand function, in the integrand the sine function is involved, so this is in terms of sine, so we have to go for the sine integral formula. Suppose in place of cos, so in place of sine, if you have cos lambda x, so since cos function is involving in that function, so we have to go for the Fourier cosine integral formula. So like this we have to decide whether we have to apply Fourier sine integral or Fourier cosine integral formulas to prove this condition. So now, so we have decided we are applying Fourier sine integral formula. Now first write down that Fourier sine integral formula for the f of x. So you will get this value is equal to 2 by pi integral 0 to infinity sine px integral 0 to infinity f of x into sine pt d. This is our Fourier sine integral formula. Now here you consider this function as f of x, since the function is in terms of x, so you consider this function as f of x. Now once if we observe this RHS part in this one, we don't have the f of x here. Instead of f of x we are having f of t. Now by using this function you try to get the value of f of t. Just replace x with t, you will get f of t function here. And one more thing, if you observe this problem here, so we have the formula in terms of p, but here we don't have the p here. So in place of p, so once you observe this sine px, here we are having sine lambda x. So here x is okay, we don't have any problem with x, and sine is also okay, and in place of p here we are having lambda. So we are having a standard formula in terms of p, but we have to prove the condition in terms of lambda. So now in order to convert that p in terms of lambda, you replace this formula with replacing this p with lambda in this formula. So wherever we are having p, replace that p with lambda, then we can get our required one here. So this is 2 by pi integral 0 to infinity sine lambda x integral 0 to infinity f of t into sine lambda t dt, and dp is replaced with d lambda. So you consider this as equation 1 here. Now what we have to do is, our task is we have to get the f of t and replace that f of t, and out of these two integrals we have to evaluate one integral, and that integral must be, we have to prove this one. Now let us see. So here this is the function we have considered, f of x is equal to this. So by using this function we got the value of f of t. Replace that x with t in f of x, we will get f of t. Now replace this f of t value, substituting these two in equation 1, we will get this equation. So now remove these brackets here. So integral e power minus at into sine lambda t dt, and the integral of second term integral 0 to infinity e power minus bt into sine lambda t dt, and keep this lambda as it is, because whatever the condition we have to prove in the problem, that lambda is p, d lambda is remaining. That means we should not apply the integration with respect to lambda. We have to apply the integration with the remaining variable, that is with respect to t. So now we have the standard formulas here. So here, suppose if you remember this standard formula, directly we will get our integral value. Otherwise we have to go for the integral e power minus ax into sine bx dx, which is equal to e power minus ax into ax by a square plus b square into that formula we have to apply, and then we have to substitute the limits 0 to infinity. So we are having, whenever the limits are 0 to infinity and the function is in the form of e power minus ax into sine bx or cos bx, directly we can use this standard formulas here. So without taking this formula, directly we can remember this formula. This formula is applicable only whenever the limits are 0 to infinity. Okay, only for these limits this is applicable. Now substitute this. Now you compare a and b and replace in this. So here we are having sine, so you have to apply this formula. So b in place of b is nothing but lambda, so lambda by lambda square plus a square minus lambda by lambda square plus b square. Now simplify this. So this is the value we got. I have taken that lambda outside. Now simplify by taking the LCM here. So finally, so you keep the variables lambda inside this integration, and the remaining we can take that outside that integration here, since that are constants. So this is the condition we have to prove here. So replace f of x with this value what we have considered at the beginning. So this is the condition what we have to prove. So this is the way how we can apply this Fourier sine integral, how to identify whether the problem belongs to Fourier sine integral or cosine integral. This is the important. So now let us take one more problem on this Fourier sine and cosine integrals. So this is the condition you have to prove. So now in this problem also he has not mentioned that particular method whether we have to go for the Fourier sine or cosine integrals. So just he has mentioned using Fourier integral show that this function is equal to this one. Same as usual. So we have two cases, Fourier sine and Fourier cosine integrals. We have to decide out of these two, we have to decide one formula. So for this we have to move towards RHS side in the given condition. We have to identify the trigonometric function which is in terms of x. So here we are having a trigonometric function in terms of x is that is cos. So on the inside the integral we are having a function in terms of cos, so we have to go for the Fourier cosine integral formula. So since the integrand on RHS contains cosine term, we use Fourier integral cosine integral formula. So now you take that Fourier cosine integral formula here. So this is our formula which we have derived in this previous slides. Use that formulas. So here also you follow the same procedure what we have followed for the first problem. So here we have to prove in terms of lambda, but here we are having in terms of p. So now what we have to do is replace that p with lambda here in this formula. You will get this formula by replacing p with lambda. Now then replace that f of x value, f of t value. So this is the value of f of x. From this you get the value of f of t. You substitute that value in this equation here. Now here we are having inside that integration we are having cos a cos b. So originally we are having a formula of 2 cos a cos b. So we don't have 2 here. You send this 2 inside this. So 1 by pi integral 0 to infinity cos lambda x into this one 2 cos a cos b. This can be written as cos of a plus b plus cos of a minus b. Use that formula and simplify this. Follow the same procedure, split this function and apply the integration separately for each term between the limits 0 to infinity. So here also we are having integral 0 to infinity cos bx 0 to infinity e power minus ax into cos bx. Use this formula directly, we can get our required value here and simplify this. Expand this lambda plus 1 whole square and similarly lambda minus 1 whole square. You will get these values. Take the LCM here and simplify. Finally you will get this value here. So take the constant terms outside that integration. Finally this is our required. In place of f of x, replace that f of x value here. So this is the way how we can apply this Fourier cosine integral formula here. So in this we have discussed what is when we can apply these Fourier transforms. For each type of functions we can go for the Fourier transform. What are the applications of Fourier transform and what is Fourier integral theorem and what is Fourier sine integral and Fourier cosine integrals, and we have taken some problems on both Fourier sine and cosine integral theorems. Now in the next video we will go for the infinite Fourier sine and cosine transforms here. Thank you.